Let us look at graphs of quadratic functions. Now, the simplest quadratic function that I have here is y equals x to the power of 2. Y equals x squared. We have the graph here. Let me make the graph thicker than it is now, and I want to see the function itself. So what this software does is label it as f of x equals x squared instead of y equals x squared. So we do have our graph here. This is a graph of f of x equals x squared, which is similar to the graph of y equals x squared. So as we can see, when x is 1, y is 1 squared, which is 1 right here. Let's zoom out. Alright, we zoomed out a bit, and we can see here that when x is equal to 2, if we go up to the curve, when we reach the curve we project horizontally to the left, what we see is that y is 4. 2 squared is 4. When we had 1, 1 squared is 1. Alright? On the left, when we had x being negative 1, negative 1 squared is positive 1, which is here. So we have these points. When x is negative 2, y is negative 2 squared, which is 4, right here. 2 squared, which is 4. When x is 3, y is 3 squared. And we go up here, 3 squared, which is 9, project across, and we see that we're at 9. When x is negative 3, y is negative 3 squared, which is 9. Negative 3 by negative 3, and so on. So we have the graph of y is equal to x squared here. Now let's talk about the graph itself a bit. Let's zoom in. Now this graph has a certain shape. The shape is called a parabola. P-A-R-A-B-O-L-A. So it has a parabolic shape. Now, this shape, it has certain applications, right? And also it has, it occurs naturally, and we're going to talk a bit about that here. Suppose this graph was turned sideways. I know that to turn this graph sideways, what I would do, right, is find the square root of x, which is the same as x raised to the power of a half. Let me zoom out. Right, this is x raised to the power of a half. I need to put the half in brackets. Put 0.5, 0.5, x raised to the power of 0.5. Alright, let's zoom back in. X raised to the power of 0.5, only the positive half you have up here, because you cannot raise a negative number to the half. So let's also add x raised to the power, negative x raised to the power of 0.5 as well. Good. So let me make these graphs, alright, in blue color, and make them thick make this in blue as well and make it thicker so you can see it easier. So this is really y equals x squared turned sideways. Now imagine that this is a satellite dish. You could have a receiver somewhere here. You have some object holding the receiver, and you have signals, electromagnetic signals coming in parallel, and it reflects onto the receiver. It reflects these signals to the receiver. These are supposed to be parallel straight lines, alright? So a dish like this, satellite dish, picking up signals from a satellite, they are shaped in the shape of them is that of a parabola, alright? They have a parabolic shape. It could also be a solar furnace where you have something to be heated, is right here, and it's reflecting the heat of the sun directly onto that object, and it can get extremely hot. So that's a solar furnace. Now that's one application of the parabola. It reflects parallel signals coming in to a single point. Now let's see where this occurs in nature. Let's erase this graph and this graph. And of course, here, if you should have signals coming in directly from straight up, they would reflect these beams, these signals at one point. So that's an application of the parabola. The other thing is this, but to make it look more acceptable, what we're going to do is plot another graph. In this case it looks like x squared, but we'll plot it upside down. So what I mean by having it plotted upside down, the question is, what would you have to do to this graph to have another graph that looks like it, shaped like this? First of all, the 1 would have to become -1. I should draw this through the -1. What you have happening here up here should happen down here. Alright? You would have to reflect every point above the x-axis below the x-axis. In other words, f of x, whenever f of x is positive, you would have to make it negative. If this up here is y is equal to x squared, what you'd have to do is plot y equals -x squared. That's what would happen. So let's see if it works. I want to plot the graph of y equals -x raised to the power of 2. It does work. So let's make this graph thicker so we can see it more clearly, and let's make the color blue. Alright, I also want to see the equation of the graph, so let me make that shown. Good. It calls it g of x equals -x squared. This up here is f of x is x squared. This down here is g of x is -x squared. So generally, the graph of a quadratic equation is in the form y equals ax squared plus bx plus c, as you remember. Now, in our case, our b is 0 and our c is 0. So all we have is y equals ax squared. the coefficient of x squared is a, means the number that multiplies x squared is a. Whenever the number that multiplies x squared is positive, we have this shape, and we have a minimum value and no maximum value. Whenever we have in the form y equal negative ax squared, the number that multiplies x squared is negative, then it's shaped like this. It goes up then down as you go from left to right. It goes, the x values going from left to right, it goes up and then down. So considering y equals ax squared, you want to move from out here to the right to somewhere out here. You would have to climb down this hill, and as you move x from left to right, you want to move from here over here, you'd have to climb down the hill, and then right at the bottom of the valley now, you're at the lowest point, and then you have to start climbing uphill, right? You're climbing up the hill. So in this case, you reach the lowest and then you start going back up. The lowest point is the minimum point, right? So this graph has a minimum value. It doesn't have a maximum value because these lines go up to infinity. So whenever you have a positive, you have a minimum value but no maximum. You don't have a maximum value. Whenever you have negative number times x squared, in this case negative ax squared, you have a maximum value but no minimum. To move from left to right, you see a hill that you have to climb over. So you have to climb over this hill, and you go up and up and up until you reach the highest point. Then you start climbing down the hill, right? So that's what you have there. Positive number times x squared, you have a minimum but no maximum value. Negative number times x squared, you have a maximum value but no minimum value. Alright, now this graph that we have below in blue, the shape of it again is that of a parabola. If you should throw a stone up like this, the stone would travel in the shape of a parabola until it hits the ground again, right? Ignoring air resistance. The fact is, if you read up on physics and the equations of motion, one of them is v squared is equal to u squared plus 2ax. You also have x equal ut plus half at squared. Another one is v equals u plus at, where the final velocity is the initial velocity plus acceleration multiplied by time. This is not the one that we're going to use. V is final velocity, u initial velocity, a acceleration, and x is the distance traveled. This is not the one we're going to use now. This should remind those of you who did physics already and did the equation of motion, remind you of something that would look familiar to you. Let's look at this one. If this here, our x-axis is in time, and this is the height, right? The distance traveled is here. Now, what we are looking at here is a quadratic equation because you have t squared. x squared, right? This is x squared, the form x squared. Our x is t, and we have half acceleration times t squared. So you basically have a quadratic equation being plotted. If you should have a high-speed camera and you capture the stone as it goes through the air at each point, every fraction of a second, like every 1/10 of a second, and you plot the graph of this, right? X equal ut plus half a t squared. Then what you'll have is a quadratic function, a quadratic graph. All right. So the shape of a quadratic graph is a parabola, and the parabola is the shape that you see when you throw a stone up in the air and it goes back down, provided that you ignore air resistance. And it also will reflect incoming parallel signals to a single point on a receiver. All right. Now, these were two quadratic graphs that we had. We had y equal x squared, we had y equal negative x squared. Suppose we look at y equal x squared now and modify it. Let's modify this. Let's make it positive x squared plus 1. What would happen? Let's zoom out and see it from a greater distance. Now, in blue we have x squared plus 1. Let us erase it. Let's change the color of our ink to blue. We have y equals x squared plus 1. What this did was to take each point on x squared and add 1 to it. So you move up at 1. When this point was at 0, this point here was at 1. They have the same shape, but each point moves up by 1. This was at 1. 1 was here. This point occurred at 1, but the corresponding point occurs at 2, where this is 2. Each point moves up 1 place. Alright? So you can see that. Let us plot a third point. Suppose we have y equals x squared minus 1. What would happen? Let's see. X to the power of 2 minus 1. You probably would expect that since x squared plus 1 take y equal x squared and moves it up 1 place, then y equals x squared minus 1 should move x squared down 1 place. Let's see if that argument really holds. Good, it does. Let us make some adjustment here. Let's make our new line green. I want to make it thicker. Good. And I also want to see the equation of it. So it's called this h of x is equal to x squared minus 1. So let's write the equation of it in green, since we have the line in green. So the green graph is really saying y equals x squared minus 1. So every point of x squared moves down 1 unit. So that's what we have. Alright. Now we're going to talk a bit more about this. But so what we'll do is just finish off this video for now, and we'll talk some more about the quadratic graphs in other videos.